Good morning, everyone. So welcome to our seminar today. And we are happy to have Professor Romeo Ortega from Mexico. And so if you are working on control theory, in particular in adaptive control and nonlinear control, I guess you know his work and also his name. So, but I'd like to say a little bit his academic path. So Professor Romeo Ortega was born in Mexico. He obtained his bachelor degree in electrical and mechanical engineering from the National University of Mexico in 1974, and then got his master degree in engineering from Polytechnical Institute of Leningrad, Soviet Union in 1978, and then the PhD degree from Polytechnical Institute of Grenoble in France in 1984. Then he joined the National University of Mexico, where he worked until 1989. So during that period, he was a visiting professor at the University of Illinois and also McGill University. So I assume he's very familiar with Montreal. And he was also a fellow of Japan Society for Promotion of Science in 1990 to 1991. He was a member of the French National Research Council, so which is known CNRS, from 1992 to July 2020. So spent about 30 years. Yeah, so after the yeah, and where he was directeur de recherche in the laboratoire de signal de système at the Centrale in Gif-sur-Yvette, France. So currently, he's a full professor at IDAM in Mexico and a distinguished professor of ITM University in Russia. So his work his research interests are in the field of nonlinear and adaptive control, with special emphasis on application. Okay, so let's welcome Professor Romeo Ortega for his very interesting talk on sliding mode control.
Thank you very much. Tout d'abord, je vais m'excuser que je ne ferai pas ma présentation en français parce qu'il y a des gens qui sont connectés à l'étranger et ils m'ont demandé de le faire en anglais. So, je m'excuse. À Québec, je fais toujours mes présentations en français. Mauvais français, mais ça va. Merci beaucoup. Well, I would like to thank Bowen for the invitation. It's a pleasure to come to Montreal again. I was here 30 years ago, as Bowen said, and my son is living here. He's a Canadian citizen. I have now a Canadian granddaughter also, so I'm very proud to have this kind of family, and it's a pleasure to come to this country. Well, this first, let me get just a few words about these flags that's standing in there. I think I don't need to give any explanation why we all should do something about this massacre that is happening in this country, and the least I can do is to put a flag and say that I regret it terribly, and every time I can talk about it, I will do it, trying to defend the right of these people who have been under genocide for years already. Okay, so the talk is, as you can see, a little bit provocative. It's on purpose, and one of the reasons is that I feel that this field is taking too much space in our community, and it's very easy to publish. That's why the people jump immediately into that topic. I actually have a sentence that I love from Vadim Mutkin, who's the father of this field. Once he told me, you know, Romeo, why sliding modes and model predictive control are so popular? And I said, why? Because it's very easy to understand. So you don't need to know any differential geometry or algebra. You just put a relay and that's it. Or write some code, some lines of code and make model predictive control. So I think that's basically the reason why it's so popular. And the main message is written there. I really think that the formulation of the problem in sliding mode control is not compatible with what we do now in modern engineering practice. And that's bad for the students because we're teaching them a wrong formulation of the problem. So that's the main message. So let me start with a modern viewpoint. It's not my generation, but artificial intelligence viewpoint. So I asked ChatGPT, which you all know, about sliding mode control. And that's what I said. Force the system into a SR manifold and keep it there. That's it. I don't care about your exact model. Get into this surface and behave. So that's basically what, and you will see in a minute, the mathematical formulation of this field. It's just designed some function that they want to make it attractive and invariant, and force the trajectories to go there, independently of what the structure of the system is, or it doesn't matter. Just force it to go there and try to go there as fast as you can, hopefully in finite time. And to do that, you put an infinite operator, which is a relay that I teach my students in undergrad. So I teach undergrad in Mexico now, that there are two reasons for instability. One is a phase margin, and the other one is the high gain. So if you put an operator of infinite gain operator, well, you're in trouble. You're actually reducing the margin of stability, and that's simply unquestionable. Even if you try to hide the relay behind some integrators or so, it's always an infinite gain operator. I kept on asking ChatGPT. I became dependent on ChatGPT completely. And I like this, put this in yellow, smash uncertainties with switching. And that's basically what they do. And then I said, okay, you compare with some other strategy. Really, I promise I didn't write the word passivity-based. It was itself ChatGPT who wrote passivity-based control, and compare it with sliding mode control. In sliding mode, you enforce the behavior by dominance. In passivity-based control, you achieve the behavior, but cooperation with physics. So I think this is a fundamental difference. Okay, I'm, of course, you probably know, I'm an amateur of passivity-based control, and that's been my field for over 30 years now. I would like, if you allow me, to talk a little bit about my personal experience with sliding mode. As Bowen said, I studied in the Soviet Union, and I studied at the time when this was starting. It was not called sliding mode control, it was called variable structure systems. And in my faculty, the head of the faculty was Laurier, the famous Laurier. So it was a good group, but they were working more on teleoperators. At that time, they were very excited with this. And they tried to apply, this is the textbook at that time of Emelianov. Suddenly the name of Emelianov disappeared. I don't understand why, but nobody talks about him anymore. And at that time, they were trying experimentally, the other students, using sliding mode controls on teleoperators. And I remember it was used to be called the sparking room, because the relays, the technology in Soviet Union in the 70s, you can imagine it was far from being very modern. So it was mechanical relays, and you could hear the clacking and the sparking and with the chattering, and of course the burning relays. So from my experience, it never worked. And actually later, I was excited because it was an interesting topic. I joined the Polytechnical Institute in Mexico, and my two first master students, I put them to work on that. I said, okay, let's work on sliding mode control and practical implementations, motor control, thermal processes, and so on. And again, it didn't work. So working with a colleague, my first paper, my second paper, the first paper was reporting that it didn't work, which is number one over there. And the second one was a paper that we claim to try to reduce chattering. This is my first Automatica paper in 1984, before either one of you were born, in 84. And that was a useless attempt to reduce the chattering. So it's just basically what we propose is to define a cone around the surface. At that time, there were linear surfaces. And then you define a cone, and inside the cone, you apply what now is called equivalent control. But that doesn't solve the problem. That doesn't make it, just makes it bigger, the chattering. So then when I started my doctoral degree, that's an interesting story, if you allow me to make this little digression. My first international conference was in Brazil, was the Brazilian Control Conference, and the plenary speaker was Joan Landau, that you probably know from Adapt Control. And he listened to my talk, and he was very excited. He said, this is very exciting. He was completely new. Nobody knew about it in the West. It was before Kokotovich and Karkion de Jong and these guys jumped into the topic and made it popular. At the time, nobody knew about sliding mode control. Nobody. Actually, we had troubles to publish the paper because they didn't understand what we were doing. And then Johan, he told me, come to France. What are you going to do? Come to France for your PhD. And he offered me an extra salary. He even told me I'm going to go for a sabbatical year in Berkeley, so you can take my office. I said, okay, man. So Everyone was very jealous of me because I had an extra scholarship and in the office of the boss and so on and so forth. It didn't last because, you know, the French, they eventually kicked me out of the office, but at the beginning I was there. So I ended up in France, and Johan, he was excited, but it didn't last very much, his excitement. He said, okay, let's try to do adaptive sliding mode, and it never worked. And then we just moved to purely adaptive mode, and we dropped the field. So, okay, these people might say it's the beginning of a young researcher. I was 25 at the time. My first report, technical report, was a report in the Polytechnical Institute, was about sliding mode control again. So I did some work in my youth on this field. So, okay, what I did is I collected from the literature a series of introductions and problem formulations. And this yellow marker, I don't like to put yellow because it's very distracting, is because I presented this before, actually in Mexico, and they said, you are making judgments out of a few papers from people who nobody knows. Well, all these papers, the 3 or 4 I talk about, are from the leading researchers. So one of them is the former chairman of the technical committee of IFAC in a very structure. The other one is the current chairman of the variable structure conference that's going to take place in the UK in December and June, I think. So these are leading researchers. I didn't put the names because I don't want to get tomatoes on my head. This you can imagine in Mexico it created a lot of upheaval, I should say. So what is the procedure? First, rewrite the system as a good term plus a disturbance, and you decide what is good and what is bad according to your prior information, which is going to be assumed very, very, very strong. And then this disturbance, you will see in a minute in the slides, is assumed to be bounded. And sometimes in the derivative of the disturbance is bounded, and you know the bounds. So you extract some d of x, and the d of x is bounded, or d dot of x is bounded, and is bounded by some non-function that you're going to use in your relay. Okay? Then you select the function out of the blue that you define sigma of x, let's say, and it's going to be your sliding surface. Okay? Then you add a relay to dominate the disturbance. So you want to put the gains of the relay functions of these prior bounds that you assume you know, and you want them for sigma, sigma dot. This is it. If you look at the papers, this is it. 95% of the papers do this. Okay? With different disguises, but it's always the same. So let me mention some papers. This is an IFAC paper online. It's a tutorial paper. It's called Survey on. So they start by writing this equation, okay, well, in the normal form. It's already, Isidori himself says that it's very, very difficult to transform a system into a normal form. You have to solve PDEs and so on. But let's assume that you manage to put it in normal form, zero dynamics, and then these guys. And these guys, you then go and assume, I may be blocking, no? Go and assume that this B is bounded from below and above, of course, larger than 0, that this A is bounded, and you know these numbers. You know K, M, and C. Okay? And then they dare to say things like, this is the global version is had to be satisfied. Of course, it has to be satisfied, but it's reasonable in a compact set. Okay, because they say we're working with physical systems, so it's compact. All the variables are bounded. But then when you go and look at their simulations, they never put the bounds. They never put the bounds. So they say it's bounded by assumption, and that's it. And then you look, if you look in, I had a student who repeated some of the simulations. The states go to 10 to the power 25, and so it's bounded, but to 10 to the 25. So that's usually the scenario. This is another one from International Journal of Robertson Nonlinear Control. Again, pulling out, this is a nice guy, so minimum phase and so on. And then this guy, it has a KP here and a D, and then you want to assume that the T is bounded by known functions. And the T is bounded also, and the D is bounded. And you use these 3 functions in your slates. So I wonder, where do I get these systems that have these science properties? Then they dare to to try to apply this to physical systems. And for instance, in mechanical systems, this is a transactions paper in 22, so it's quite recent. Okay? And they pose a problem that was solved 20 years ago, which is output feedback global regulation. This paper was tracking, sorry. This paper was solved in transactions 2015. But again, they say, okay, let's try to do it. And then they start, I couldn't write all the assumptions. It's like 2 pages of assumptions. But one of the critical assumptions is that the gravity function here is 0 only at 0. So this means that any mechanical system which has rotating angles is not qualified, and the only equilibrium that you can stabilize is this equilibrium. And the example they have, literally, is a hanging pendulum. So you want to place a pendulum in this position, and you want to do a controller to put it in this position. You could just drop it, and we'll go there automatically. But this is it. This is it. And then they make another strange assumption. There's a partition of the inertia matrix in this form. These are the unactuated coordinates, and this block is constant. We proved, we have a book on PID, PVC, passivity based control, where if you have this assumption, the robot can be controlled with a PID, globally convergent PID, just with this assumption. So this is, sorry to say, but this is quite ridiculous. Then, again, they write it as a nice guy, a chain of integrators, and then disturbances. And again, now they assume that the derivative of the disturbance is bounded. And then they say this means that acceleration and velocities are bounded, which is fulfilled in physical systems. So, I mean, I really wonder who reviewed the transactions paper with these kind of assumptions, knowing particularly that that problem was solved 20 years ago. So, okay, so that's my main concern. Now, recently, I'm sorry, I shouldn't move from here. Recently, Transactions 26, a regular paper in Transactions 26, yeah, they claim that they combine passivity. I'm sorry to say, because this is my very good friends, Arjen van der Schaft and Jacqueline Scherpen, and so, and I'm going to Groningen in 2 weeks. I'm going to present it, and I'm sure they're going to be very upset. But I told them already, look, this is ridiculous. Why are you doing this? And the answer of Arjen, which is my very good friend, he said, actually didn't check it. I didn't check it. It was just the first author who came, and it was very convincing. An Italian guy, you know, these Italians, they're very, very easy to convince you with bluffing. And they said, just add a relay. Okay, just add a relay. Okay, so that was the problem. The problem, you have a Hamiltonian system. Okay, let me go back. Classically important Hamiltonian form. I'm sorry, I'm pushing the wrong button. Written in important Hamiltonian form, classical. You again extract the nasty guys. These are going to be nice. You're going to see in a minute. And then you define the trajectory. This problem, we show that this problem is mathematically untractable. If I give you a nonlinear system and you want to find the trajectory and compute the U star that will achieve this trajectory, this is an inverse problem, very well known in mathematics, that is in general not solvable. Even for very simple dynamical systems. So for this system, I really wonder where they're going to get the U star and X star. But let's say that they got it. Okay, they got this U star and X star, and then they go again, write it as a nice guy and some disturbances. They define the surface out of the blue. After 5 impenetrable assumptions, they say, let's define the sigma in this form. And this sigma has a nice property that is the sum of these 2 functions whose bounds I know. I know the bounds of this function. This phi, I know the phi bar. The gamma, I know the gamma bar. So it's just saying, I sorry to say, this is quite ridiculous. And then they have 3 physical examples: a levitated ball, 3 tanks, control of tanks, which are trivial examples that we solved 20, 30 years ago without assumptions. So this is the material that you see in the literature. And we're talking about the regular paper in Transactions 26. So it's really very, very sad. Okay, I'm a little bit uncomfortable here. Okay, now, of course, you never see the inputs inside remote control. And there's a very good reason for it. Because if you take a very simple example, a double integrator. And you put one of these sophisticated, this is called a high order sliding mode. And well, you see the behavior of the trajectories of the X2. Okay, it's an output feedback control. Okay, and of course the sliding mode is like that, very well. And you look at the input, this is input even without noise. If you look at the input with noise, simply, well, the computer had to stop every so often, and you need this integration step up 10 to the minus 35 to do the integration. And then if you look at the effect of the input on the tracking of the output, sorry, you get this behavior, which is 20% of the actual value. And this is just a simple PD, just a simple PD, so static state feedback. So that's more or less the situation always. Let me show you some experiments. We did some work with colleagues from the north of Mexico, a town called Torreon. They have very good lab on robotics. And I proposed to them, let's take the simplest robotic system you have, which is just a pendulum, and let's try to apply sliding mode control and see what happens. Okay? And then compare with another controller, which is this immersion and invariance controller that we developed, sorry, I was pushing the wrong, developed several years ago. So it's a simple mechanical system with friction and this output feedback. So you only measure position, you don't measure velocity. Okay, so this is the system. You see, this is the dynamics. This is the model of the friction and the mechanical part of with the gravity force and so on. And you assume the parameters none, but you only measure Q. You don't measure Q dot. Okay, and we took from the literature. Actually, this again, the co-authors are the former chairman of the IFAC technical committee, and as another very famous professor in this field. This is from 2006. This is their controller. It's an adaptive controller where they claim they can estimate parameters and so on and so forth. Okay. So let me not go into the details. This is our I&I, immersion and invariance controller, which is more or less a standard. And we have a global stability proof for this scheme. The previous controller relies on an assumption of persistence of excitation. So this sort of regressor has to be persistently exciting. And the I&I does not need this assumption. Okay. So these are the experimental results, taking the numbers explicitly from that paper. So we didn't fiddle around with the numbers or so on. So this is the error in velocity. Red is, of course, the I&I, and red is the sliding mode, and blue is the I&I. You can see the behavior. You can see the behavior of the parameters are biased, and actually, they are diverging. If you let it run, they will diverge. And we'll see in a minute that actually this happens. This is all experimental data. This is the behavior of the speed and its estimate. Again, red is sliding mode, blue is not exactly zero. This is a physical system, there's a mistake. But if you compare the size of the transients, is really overwhelmingly superior. Okay. Now we put a controller. This was just observer. Then we put a controller, which is a very simple controller that is going to transform the system into a chain of integrators with some gains. And this is the full information control. Okay. Cancels the nonlinearities and so on. And the surface equivalent control. Then we tried the desired trajectory, which is this exponential. It's a non-rich trajectory, so it does not satisfy the persistence of excitation assumption, so it does not fit into the theory. But we want to see how was the behavior. Well, you see the behavior. This is the sliding mode, this is the I&I, and then this diverges. This simply goes to infinity. So this is experimental evidence. We didn't trickle too much with the data, but that's what we saw. And it took the student a few weeks to get this working on. You compare here the X2 for the sliding mode control, and for the data control, it glues, it literally follows the speed very well. And position tracking errors. And the control signals, of course, the control signals in the sliding mode are full of noise, as expected. Okay. Let me skip this. I think I have time. There is a book, a recent book, and an IFAC survey paper published in 23, so a few years ago, where they claim that there are 5 generations of sliding mode control. And I think this is a narrative of 5 generations of sliding mode control. Because all they do, if you look at the 5 generations, so the first one is put in 81, you have directly the relay here. Then they call second generation is replacing the relay by some boundary layer. This was done actually by Slotin and Canudas in the 70s, I think. Then started the work of this gentleman, which is sort of the idol of the community, and a mathematician from Israel. And then what he did, he added an integrator. Basically just add an integrator and put another relay. And put a weight, which is a fractional power. They call this the third generation, the super twisting. The fourth generation now is more clever because now you add more integrators. You make sigma, sigma log, sigma, and so on and so forth to be attractive. And this leads to this kind of controller, where again, of course, you have this signum, and now you have these complicated expressions. Again, these functions, fractional power functions, they grow to infinity at 0. So they add to the problem of injection of high gain. Okay. So that's it. And the 5th generation, I didn't have patience to go through it. It's just a kind of recursive application of this. First this one, the second one, so on, and then they recursively apply this. So these are the 5 generations. And as I said up here, it's just moving the relay around. The relay from here to here, add an integrator, put the relay someplace else. Okay. Now let me talk briefly. I'm actually going very well on time. 45 minutes, huh? Yeah. Let me talk about current engineering practice. I have been working with the supervisor of Professor Choi here with motor control. I work with people from power electronics in the University of Colorado, Denver, with people in power systems in Northeastern University, George Burgess. So people who know about the field and actually are applied researchers. They work on that field. And what we did is collaborate with them. My students used to spend, Bowen didn't do that, but all the other ones used to have 2 supervisors, one supervisor in applications and myself, and then they would spend 1 month, 6 months, up to a year in the institution where the other guy worked, and they did experiments over there, okay? And this was done with Boston University, with Virginia Tech, and even some French institutions, okay? So that's my experience. So let me talk about current engineering practice. Now, I think you have a group of robotics here. So in robotics, the dominant technique to regulate the position of robots is the so-called Takegaki Harimoto PD controller. So it's a PD controller that exploits the passivity of the robot from torque to velocity. So it's a physical property that's been exploited for the design of this controller. For tracking, it is unquestionably the Slotin controller, where now the physical property that you exploit is the skew symmetry of this matrix. This is well known, was established by Spong and myself, and Kodicek in the US, that this matrix is skew symmetric. Okay. Now in teleoperators, Anderson and Spong, and later on Slotin, had this very clever idea of transforming the teleoperator into a traveling wave. Actually, with Professor Nam, we did the opposite. In Korea, in post-tech, they had this problem they call overvoltage. So they have very long cables from the ship to a drilling machine in the base of the sea. And these very long cables, when they introduce high power, high technology switching devices, the IGBTs, then they started sending very high frequency signals. And then the cables, these long cables, they behave like traveling waves. So they had this phenomenon of the wave traveling back and burning the motors. This is a very serious problem. I still, until now, is not completely not completely solved. So they were burning the IGBTs, they were burning the actuators on the ship. And it's exactly the dual. In that case, you have the traveling wave. And what we did with Professor Nam, we actually have a patent with him, is to transform it into delays, into pure delays. So again, you're using the physical properties, the practical property that you have a traveling wave. You see, it's not writing at F plus D and D bounded. And then there's also, in pendular systems, I think the dominating technique is this energy pumping and dumping by Spong, okay? And some work with Bowen on assigning an energy function that does not have a minimum, but it has the shape of Mexican sombrero, okay? So it has the shape of Mexican sombrero, and then the minimum is along a trajectory. So you force the trajectory to live in this surface, and then it creates the periodic orbit. So that's a very nice work of Bowen. And I think it's been used. It's been used by people. Now, for non-holonomic systems, there was a major breakthrough by Sordalen in his PhD thesis, and later Astolfi, using time-varying gains. But these time-varying gains are dependent on the structure of the chain system. So it depends if you have, I think it's called singularity 1, singularity 2, then the gains are different. So you have to look at the structure of the system to determine the gains. So that was actually, this is the paper, the most cited paper of Astolfi, and he's very proud because he said there's a Japanese chip, which is called Astolfi's controller, and it's a chip that is used commercially in the mobile robots. So it's again, this technology that is developed based on the physics of the system, and not on dominating or so. In motors, I'm afraid to talk about motors in front of this expert here. In electrical motors, the dominant technology is called field-oriented control. I think it's in induction motors is the dominated technology. And again, it's a technique that is based on exploiting the relationship between flux and voltage in a rotating frame. So trying to put them in phase and synchronize the flux and the voltage. So again, it's really exploiting the physical structure of the system. And we proved that it's equivalent to passive systems, the passive system interconnection. So again, we have a physically motivated strategy. There's another strategy which is called direct torque control, which was these two people, by the way, are people from industry. They Hassan and Blanke and Deppenbrock, they were both working in companies, so they are not mathematicians, they are not top-line relays, and they are looking at the physics of the system. And it's based on an adequate switching of the hexagon of points that you visit in a bottle. And finally, in power converters, the industry standard is something that was introduced by a Japanese researcher, again, not a mathematician, Akagi. It's called instantaneous PQ control. And we proved recently again that it exploits a property of passivity, but it's a different property of passivity. It's called shifted passivity. So I talked with Takagi a few years ago, and he was very surprised. He didn't understand. Neither Takagi. I remember talking with Arimoto at the time. I was visiting Tokyo for 1 year, and I had to explain to him what passivity is. So he didn't know what's passivity, but he understood that he was using some physical properties of the motor. And the same thing with Takagi. Okay. Finally, in power systems, the original turbine governor control of synchronous systems, which has led to what is called this droop control, is again based on a physical property, the relationship between frequency and speed. Okay. And recently, in this very interesting series of papers, George Weiss introduced with the inclusion of more and more power electronics in the power systems, the previously existent of inertia, the rotary inertia disappeared. So they call that now inertia-free or inertia-less system. So this inertia was important because when you had a lower demand than the offer of energy, you could store the energy in a rotating device. So the rotor will be played like an accumulator, if you want. So it will store energy. But now you don't have that. So you don't have that. So what do you do with the excess of energy? Well, they're burning towers. They are actually here in Quebec. You in Quebec, this Quebec Hydro is pumping the lake, pumping a lake in order to increase the kinetic, the potential energy, and then lower it down to extract the energy. So this is how energy is structured now. So the idea of George Weiss is to emulate a rotor via a control of the converters. And he called this, it has a name, sync converter, okay? So all these strategies, why am I bringing all these? Because all these exploit the physical structure of the system. And they are the existing dominating engineering strategy. So these are my concluding remarks. So given that engineering practice is dominated by control schemes that preserve and exploit the physical structure, so what is the interest to study schemes whose first basic step is to destroy the structure? So you're contradicting engineering practice when you do that. And more dangerous is the fact that we're training a new generation of engineers with a technique that doesn't have an impact. In my case, I'm personally concerned because we were looking at the statistics the other day. 60 to 70% of all the PhD theses in Mexico in the last 10 years have been on sliding mode control. So 60 to 70%. So the whole generation of engineers is being trained to do this. And this for a country like Mexico is catastrophic because these guys, what are they going to do? They're going to keep on publishing papers and they will never join the engineering practice, okay? Or have an impact in engineering practice. And this for me is very important. Scientific publications. I had a series of exchanges of mails with the three former editors-in-chiefs of the three most important journals, with Miroslav Kristich, with Alessandro Astolfi, and with Andy Till. So we had a chatting group, in some sense, a few, like 4 or 5 exchanges of mails that I started. I said, we have to control this. There are just too many papers on this topic of very low quality because there are a lot of reviewers from this field. And it's a self-inseminating society. So they just support themselves. They publish more and more and more and more. So then the reaction was, I brought to them the history. I was a member of the editorial board as an editor at large in Transactions in the 70s, early 80s. And at that time, there was something called fuzzy control. You probably have heard about that. And we were getting in Transactions a lot of papers on fuzzy control. So at that time, there was a Greek guy, Panos Antsakis, and he talked with us and said, what should we do? And my proposal was, let's call the leading researchers. There was a guy, Loftus Sade, that you probably know, a collaborator of Charlie de Sauer in Berkeley, who was the initiator of fuzzy control. And we had a meeting with him, literally. And in the meeting, the proposal was, create your own journal. IEEE will support you. Let's create a fuzzy control journal, and you publish there. And that's what happened. That was 25 years ago. So they created this journal, and the papers from fuzzy control disappear from Transactions. The problem now is, and this was Alessandro, as usual, in a very bold manner, said, it's impossible. It's impossible because we have 10 editors out of 30 which work in this field. So what are we going to do? We're going to kick all these associate editors. It's a powerful society, not scientifically powerful, but powerful in an effective way of controlling the editorial boards. So that's the end of my story. Okay.